நம்ம இந்த ஹெவி
Hello, Jagan.
Yes, sir.
Are you?
Vanakkam.
Sir. Vanakkam. Jagan.
Yes, sir.
What about the IC engine? Yeah, internal combustion emission notes. Are you prepared or not?
No, sir.
No, சொல்றதுக்கு என்ன நோ ரெடி பண்ணி கொடுப்பா சீக்கிரம் எல்லாம் படிக்கணும்ல.
Okay, sir. Okay, sir. Okay.
Sir, just one another.
Jagan, can you switch your camera, please? Switch on your camera, please, once. Yes, it's a request.
No, yaar, abhi office pe ho yaar.
Just for a second, then you can switch it off. Thank you so much. Please capture the screen. Please capture the screen. I have captured it. Okay.
No. You are asking Jagan, na?
Yes, sir. Actually, I was just trying to see how he looks now nowadays.
No, I have not seen it. Where he is?
Sir, same as before, sir. Nothing different.
Jagan, உங்களுக்கு இவ்வளவு ஃபேன்ஸா?
ப்ரொஃபசர் வந்துருவாருப்பா.
நீ இப்ப ஜெகன் நீ வந்து எப்படி இருக்கா நியூஸ் ஒரு நியூஸ் ரீடர் மாதிரி ஆயிட்டியா? பயங்கரமா.
Thank you, sir.
படையெல்லாம் தான் சொல்லுவாங்க.
Fits, sir. Rajam sir, see the way it
sits. He sits like a BBC news reader.
Yeah. There is no doubt about that.
But he is sitting in London.
Multiple monitor. No, multiple monitor.
That is what I'm saying.
Yeah. Keep the screen.
That is what we are saying. In BBC London, there are multiple models.
Thank you, sir.
And when he smiles, they dimple on his cheek, you know. When he smiles, they dimple on his cheek. It is a sign of very high fortune.
Yes.
Suspiciousness, actually.
Thank you, sir. Thank you.
No issue. Okay.
Polama.
Arun sir, your favorite color is?
No. Something, whatever my wife is giving, I wear it and come up. White, green, some yellow, all these things are there.
Mr. Hassan is in Pune. Actually, I was supposed to meet him yesterday, but I got one urgent work, so I could not meet him. I will try to meet him today.
Arun sir, you came to Pune?
Yeah, I am also in Pune. I am sitting in Mahindra Towers right now.
Mahindra Towers. Okay.
Hey, sir, then please meet us now. Then where are you now?
Right now, I am in Mahindra Towers.
Where are you staying, sir?
Huh?
Where are you staying?
Where are you staying, Arun sir?
I am in Nuria Hotel, Nuria, Adit Birla Hospital, opposite to that.
Oh, okay.
Arey, sir, it's very near to my home. I'll come to
Welcome,
meet you. I'll come to meet you.
Right. I try to go meet you. This week I will be here only.
Next plan, we all can meet together.
Yes. Sir, Adit Birla Hospital is very near to my home, so you can come to my home for dinner if you want.
Let's see. Here, work was not completed.
Sir, I think even the work is not completed, you will have dinner, na? You will not skip the dinner because of work.
Yes, sir. I will be there in the week. This week, we try to meet you.
Okay, then Hassan and you both are invited.
Right.
Yeah, we'll meet together. Hello, am I audible?
Namaste, sir.
Yeah, audible.
Good evening. Yes, sir.
Good evening, sir.
Namaste, sir.
Is my screen visible to you?
Yes, sir.
Yes, sir.
So there is some problem in recording this lecture, but I will see how to fix it. We will go ahead. Please answer your attendance. Aditya Kumar.
Present, sir.
Anand.
Present, sir.
Ananta Kumar.
Present, sir.
Arnachalam.
Yes, sir.
Hasan. Present, sir. Hemant.
Present, sir.
Jagan.
Yes, sir.
Kesav Prasad. Kesav Prasad.
He is not there, sir.
Okay. Lakshmi Narayanan.
Sir.
Prabhakaran.
So Prabhakaran is present, sir. Mike is having issues raising hand.
Okay. Prem Vinayak.
Present, sir.
Rahul.
Present, sir.
Roshan Kumar.
Present, sir.
Sabish Kumar.
Present, sir.
Satish Kumar.
Present, sir.
Titus.
Present, sir.
Pallish.
Yes, sir.
Vigneshwaran.
Present, sir.
Jayraj.
Present, sir.
Vikash.
Present, sir.
Vivekanand.
Present, sir.
Yadav.
Present, sir.
Yuvraj.
Present, sir.
Okay, so Kesav Prasad is absent today. Okay, so based on your request, I have discussed with the coordinator. I have given you the schedule for the exam and mode of conduct of exam for ME6162W. So as informed to you, quiz 1 and 2 will be conducted in IITM for the students who are here in Chennai. For outstation students, I think 3 of you, the exam will be conducted at TCS Center. The details about the mode of conduct and venue will be informed to you before the exam. End semester exam will be conducted only in IITM for all the students, as informed to you, and the dates are also announced to you. So you will have your quiz 1 exam on March 2nd, which is on Saturday, 10 o'clock, and quiz 2 exam will be by April 6th. So again, it was originally planned for April 13th. I have preponed it based on the request from Hasan. So April 6th, you will have your second quiz. End semester, welcome. The end semester exam is on May 5th. Okay, May 5th, it is on Sunday. End semester exam will be for 3 hours. The quizzes will be conducted for 50 minutes for 30 marks. Okay, 50 minutes is the duration for the quiz 1 and 2. End semester exam will be conducted for 3 hours. Fine, I hope you have noted down this schedule, and I hope you don't have any other problem with regard to the schedule as well as the mode of conduct of exam. So we'll go ahead with that. Do you have anything to say?
It's perfectly fine, sir, for us. No issues.
Fine. Okay, very good. So let us freeze these dates and the mode of conduct of exam, and we'll go ahead with that. Okay. And then there'll be 2 assignments. Assignments, you can submit it to me over email. I will evaluate and send it back to you. And so as informed to you in the introduction sheet, you will have 2 quizzes and 2 assignments. Quizzes weightage is 20% each. For assignment, 10% weightage for your grades. And end semester exam, it will be 50% weightage. Okay, so that is how you will be graded for the course. So make a plan, and I have already shared the material. I have also given you the references. So you can start preparing. And if you have any doubts, as always, you can let me know over email. I will get back to you. Okay. So with that note, let us get started. So we are in chapter 2. We are now discussing about thermodynamics of combustion. Before we discuss actual combustion event in spark ignited engine and compression ignited engine, here we are discussing about the thermodynamic aspects of combustion. Initially, I started this chapter with a discussion on why we are doing this, why we study the thermodynamic aspects of combustion. As said to you, combustion as such is very complex in SI and CI engine. I have given an overview of how the combustion event is happening in SI and CI engine. It's just an overview. Detailed information will follow later on. Okay, so what we understood is SI engine combustion is flame propagation based combustion. CI engine combustion is air fuel mixing control combustion. Nevertheless, in both the combustion event, the flame movement in SI engine and the mixing, rate of mixing in CI engine, which is going to control the combustion event, is not well understood. Okay, because the process is highly unsteady, and it involves very high temperature, and it involves very small time scale. It's a combination of high temperature, small time scale, which makes the combustion even more complex to resolve it completely using any experimental techniques. Okay. So we have a limited understanding. That's why we say that we have a limited understanding about the combustion event that happened in SI engine. And the combustion event is what is controlling the performance of an IC engine as well as the pollutants that are emitted from IC engine. And we have only limited understanding about this. So having understood the complexity of this event, we wanted to start with a simplified thermodynamic based approach, which is a steady state approximation that we give. We focus on state before combustion and after combustion. And by applying thermodynamic principles, like I have shown here, by applying first and second laws of thermodynamics, we are going to get useful information about the combustion event. Okay, so we are going to derive some useful parameters that will help us to better analyze the combustion event. And also, we already discussed about stoichiometry. We are going to discuss about chemical equilibrium. These concepts provide us with an estimate of the composition of the combustion product. We need to analyze the composition of the combustion product. In the experiment also, we always keep track on how much of products are emitted from the combustion even, because some of these products are objectionable pollutants. So in the previous class, I discussed about this combustion stoichiometry, wherein we could get an estimate of the major species that are present in the combustion product. Okay, we get an estimate of major species present in the combustion product or product composition we can get from stoichiometry. And what is this stoichiometry? It works based on the principle of conservation of atoms or conservation of mass in a chemically reacting system. In a chemically reacting system, what we have in IC engine, when I say system, it is a fixed mass of matter. In IC engine, what is the matter that we consider a chemically reacting system? It has fuel and air as a reactant. They combust, release thermal energy, which is what we are interested in. This thermal energy is converted into work, but thermal energy that is released, it's all about the products that are released, because some of them are objectionable pollutants. So these products, there are several products. We focus on only major product. We have related the product with the reactant. We want to find the product composition. How we have done? We have related that to the reactants. We have related that to the reactants indicated here based on the conservation of atoms each present in each element in the reactant as well as in the product. Based on this conservation of atom principle, this equation is written on mole basis. It's generally more convenient to write a chemical reaction in mole basis rather than mass basis. So we have written this general hydrocarbon stoichiometric combustion equation on a mole basis. Okay, 1 mole of hydrocarbon. In generic representation, it is C alpha H beta, where alpha stands for number of carbon atoms and beta stands for number of hydrogen atoms. It combusts with air and releases this major product CO2, H2O, N2. So here carbon present in the fuel completely combusts form CO2. Hydrogen completely combusts form H2O. Nitrogen, we assume that it is coming out as it is, because it's a reasonably good assumption, because only at a very high temperature nitrogen oxidizes and form NOx. Okay, NOx include NO and NO2. And this is quite possible in IC engine combustion, because we know that the temperatures, as I said, well above 2000 K. But here we are starting with a simplified assumption that the temperatures are low and nitrogen comes out as it is. Nevertheless, in a real engine, IC engine, these are the major products, CO2, H2O, and N2. And now this B, C, and D stands for number of moles of CO2, H2O, and N2. We get an estimate of the number of moles of these major species by doing this stoichiometry. That is one useful information you get from stoichiometric analysis. Second useful information you get is you get this mass of air to mass of fuel under stoichiometric condition, which is theoretically correct proportion of fuel and air. We get an estimate of how much of air is required for the complete combustion of a given mass of fuel from this equation. This is again a useful information, because this will help us to fix the capacity of the engine or displacement volume of the engine, because you know what is the engine you need to design, what should be the rated power of the engine you are designing. So from the rated power, you can fix the fuel mass. Once you fix the fuel mass from this equation, you can fix the air mass, stoichiometric or chemically correct proportion of air mass. So, and from this, you know what is the range of V at which you need to operate the engines. And this will provide a vital information of designing or fixing the displacement volume of the engine. One major problem I would say with gasoline and diesel kind of fuel is it's a multi-component fuel. In first unit, we discuss in detail about the composition, molecular composition of gasoline and diesel. So our understanding is from the discussion, these are multi-component complex mixture of hydrocarbon. The number of hydrocarbon can go all the way up to 1000. So now in the stoichiometric equation, you need to get this alpha and beta, which stands for number of carbon and hydrogen atom. So we generally go with approximation here to get alpha and beta. That approximation is called surrogate modeling approximation, wherein we consider only few hydrocarbon to mimic the characteristic of this 1000 hydrocarbon. How do we choose this few hydrocarbon? Based on the hydrocarbon class. As we have discussed in chapter 1, this 1000 hydrocarbon can be grouped or binned under 5 classes. So you know what is a hydrocarbon class in gasoline and diesel. From this hydrocarbon class, you can fix few hydrocarbons, pick few hydrocarbon for each class. From that, you will be able to get alpha and beta, and this is called surrogate modeling approach. That is how we go ahead and simulate the combustion of these fuel in a real engine. Okay. And we need to carry out combustion simulation, which is part of your R&D activity for engine development. You cannot do without simulation work. That is how we are going to simulate this gasoline and diesel combustion. So in an actual engine, you know the air that you use is either higher than or lower than the stoichiometric proportion. Because of that, we introduce this parameter, fuel air equivalence ratio, which is a ratio of actual fuel mass to air mass, or with respect to stoichiometric fuel mass to air mass, or in other words, it can be air mass to fuel mass under stoichiometric condition divided by air mass to fuel mass under actual condition. These two equations are similar. Only thing is it is written in different forms. I prefer to use this form because it gives direct indication about how much of fuel we are using. So there are three conditions, possible condition. P is equal to 1 is what is stoichiometry, and P greater than 1 means fuel rich combustion, because P is an indicator of fuel mass. When you say that P is greater than 1, the actual fuel and air mass you use is higher than the theoretical mass. So that's why we say that you are using more fuel or fuel rich condition. And if it is a fuel rich condition, the products are going to be different. You are going to have CO and H2 apart from what we have discussed. The CO and H2 are the major products of incomplete combustion. Since you are using more fuel than the theoretically correct proportion, there is a deficiency of oxygen. Deficiency of oxygen will lead to incomplete combustion. The third condition is P less than 1. When P is less than 1, you are saying that the fuel that you use is less than the theoretically correct fuel proportion. It means you have a lean condition, fuel lean condition, meaning that you have more oxygen that is available in the system, combustion system. Because of that, you will have that excess oxygen appearing in the product. So these are the possible P values, and accordingly the major product composition is going to be different. And we also discussed that SI engine will have a P range of 0.9 to 1.1. It's very close to stoichiometry. This is because for two reasons. One, SI engine is flame propagation based combustion. To maintain a stable flame, you have to run your engine around stoichiometric condition. That is what is giving a stable flame. When the flame is not stable, the combustion is not stable, then you will have a problem of poor combustion stability and associated problems in SI engine. We want to avoid that. So we are running SI engine close to stoichiometric condition because of this reason. Second major reason why we run SI engine under this condition is three-way catalytic converter efficiency is high. Three-way catalytic converter is one of the after treatment control system that is predominantly used in SI engine, without which you cannot meet the current emission norms. I will discuss more about it in the second module about this after treatment control system. This converter efficiency, this three-way catalytic converter efficiency will be high only close to stoichiometric conditions. Okay, these are the reason why we run SI engine under this condition. CI engine, if you look at it, it's always less than 1 as shown here, 0.4 to 0.8. It's operating fee range. It's always lean. This is the overall fuel air mixture, and you should note here that SI engines are subject to homogeneous mixture combustion. Whatever we are talking, fee we are talking here, 0.9 to 1.1 will be the P value actually inside the engine, whereas in CI engine, it is subjected to heterogeneous air fuel mixture. Heterogeneous means you will have different proportions of fuel and air spatially, temporally. What is spatially? Inside the cylinder at different locations, you may have different fuel air equivalence ratio. At different time in the engine operating cycle, you will have a different fuel air equivalence ratio. This is what I mean by there is a variation in P spatially and temporally. Okay, so you have something called P local. This P local is a local fuel air equivalence ratio. This is a function of space inside the engine cylinder or location inside the cylinder, as well as time in terms of crank angle. At different crank angle instant, you are going to have different P. So you have a heterogeneous air fuel mixture in CA engine, and because of that, you end up in creating very high smoke or particulate matter in CI engine. So we are forced to use lean mixture for CI engine operation. This is one of the reasons why CI engines are always bulky or non-compact compared to SI engine. You can design a compact SI engine, but you cannot design a compact CI engine. This is exactly the reason why our motorcycles cannot be running with diesel fuel or CI principle, because they are a very small engines, right? You can have a very compact small engine working on spark ignited engine principle, but you cannot design similar engine with diesel fuel, because the size of the displacement volume of CI engine is always much higher compared to SI engines. You use up to 30 to 50% XSR. So your engine capacity is always larger in a CI engine compared to SI engine. With that understanding, now I am going to the next topic that we are going to discuss. So now we are going to see the application of first law of thermodynamics to study the combustion event. By applying first law of thermodynamics, so you have to brush up your thermodynamic knowledge here. I cannot go back and teach you thermodynamics, because that is what we are going to see here. We are going to apply thermodynamic principles, basic principles like first and second law, and we are going to derive some parameters. And these parameters are very useful to analyze the combustion event, both in SI engine as well as in CI engine. So here we are going to start with the application of first law of thermodynamics to study combustion event. When you apply first law of thermodynamics, you are going to get two useful parameters. One is a heating value. Heating value provides you an estimate about how much of thermal energy is released due to the combustion event. And second useful parameter is adiabatic flame temperature. That is a theoretical maximum flame temperature reached as a resultant of combustion. These two informations you can get by applying first law of thermodynamics. These two are very useful information about the combustion event. One is the gross thermal energy release that you get, and second one is the maximum temperature that is reached by the combustion system due to combustion event. Now let us see how to get these two parameters. So this heating value is also referred to as calorific value in some of the textbooks. It's also referred to as heat of combustion. All this carry similar meaning: heating value, calorific value, or heat of combustion. In different textbooks, you have different nomenclature being followed. Okay, so I will follow this heating value. What is this heating value? It's a quantity of thermal energy release or quantity of heat that is liberated by complete combustion of unit mass or unit mole of a fuel, and the products of combustion are cooled to initial temperature. So this gives you an estimate of how much of thermal energy is released, okay, if you burn a fuel, okay, burn a unit mass or unit mole of a fuel. So how much of thermal energy you get when you burn a fuel is given by this heating value. So here you could see that we are imposing two conditions. This is condition number one. The combustion event is complete. Second one, we are cooling the combustion product to initial temperature. So these two conditions are imposed when we define here what is this heating value. Why do we impose this condition? These conditions are imposed because it is a property of a fuel. Heating value is a property of a fuel. You know, any property should be measured under reproducible conditions. So you should get the similar value when you measure it for a multiple times. So it's a measurable property of a fuel. That's why we impose this condition. And as you know, any property are measured under control condition, because it should be reproducible. So that's why we have imposed these two conditions. So whoever measures these conditions has to be complied, and under those conditions, the heating value should be defined. Okay, that is the purpose here. So as I said, this is not only estimatable. We are going to see now how we can get an estimate of heating value by applying first law of thermodynamics. That is our focus here. But as I said, this is also measurable. The equipment that is used to measure this property is called bomb calorimeter. Have you come across this? Have you come across?
Just in textbook.
Yes, right. So this calorimeter, what is done here is a known volume of fuel is taken, and it will be combusted with oxygen in a bomb. Okay, so in a bomb is a strong vessel because the thermal energy is released, right? It has to withstand that high thermal energy release. So fuel and oxygen combust in a bomb. Bomb is a vessel, strong vessel, and outside the vessel you will have water. This thermal energy released is absorbed by water. What we do to get heating value is we will track the temperature rise in water because of the thermal energy release. So here, whatever thermal energy release is absorbed by water. The rise in temperature of water is taken as a measure of thermal energy that is released due to combustion event. That is how we get the measured value of this heating value. Now let us see how we can estimate it by applying first law. There are two conditions. One, the combustion can happen at constant volume. That is what we model SI engine combustion. The heat addition is constant volume heat addition. The other option is the combustion can happen at constant pressure. That is how we model heat addition in a CI engine. It's a constant pressure heat addition based on thermodynamic analysis. You know, SI combustion is approximated as constant volume and CI engine combustion is approximated as constant pressure combustion. So combustion even can happen under these two conditions, either constant volume or constant pressure. Now let us see how we can get an estimate of heating value by applying first law under these two conditions. So we are doing this, we are calculating heating value by applying first law of thermodynamics to a chemically reacting system. So I have just now said that a system is nothing but a fixed mass of matter. When I say a chemically reacting system, what it has is a fixed mass of fuel and air before combustion. After combustion, it will have a fixed mass of products of combustion. Okay, so we are dealing with chemically reacting system here, and we are applying first law of thermodynamics to this chemically reacting system. Now let us consider constant volume combustion, case 1. Constant volume combustion you can visualize as a combustion even happening in a rigid vessel. In a rigid vessel, the volume is always going to be same, and this fuel and air taken into the rigid vessel combust, releases thermal energy, and we are going to get an estimate of this thermal energy under this condition, which is constant volume combustion condition. So when you apply first law of thermodynamics to a system, you can write it as the general form of first law equation is Q minus W is equal to delta U. First law is actually a form of law of conservation of energy. We are just doing an energy balance here. Q is thermal energy and W is another. Here I have considered a chemically reacting system. What is this R in the subscript stands for? R stands for reactants and P stands for products. Q minus W with a subscript R to P. Reactants are converted to products. Okay, that is what the subscript is representing. Q R to P minus W R to P is equal to delta U R to P by first law of thermodynamics. And since we have considered constant volume combustion, volume is constant, so there is no displacement work here. W will become 0. You know W is nothing but integral P dV. Displacement work. Okay, so this dV is change in volume. Now in our case, in a rigid vessel, volume is constant. There is no change in volume, so W becomes 0. So Q minus W is equal to delta U R P. W is 0, so Q will be equal to delta U R to P. You can write this as UP minus UR. R negative of Q R to P is UR minus UP. And what is this Q R to P? This is called heat of reaction. Can anyone tell me what is this heat of reaction?
It's basically change of internal energy, sir.
Change of internal energy. That is what the equation says.
Right, sir.
But
the amount of thermal energy required to trigger the reaction or
Convert from reactants to products.
no, actually, the energy required to trigger the reaction or start the reaction is activation energy. We have already discussed about that. So here we are talking about conversion of reactants to product. So these reactants are becoming a source of energy, and we are tracking thermal energy released because of the combustion of reactant. So it means the reactant already possesses some energy. What is that energy possessed by the reactant? It is
Bond energy.
Chemical
yes, energy or enthalpy of formation, right? And other energy you can expect is energy due to temperature. If the reactants are at higher temperature, there may be energy possessed by the reactant because of the temperature. Okay, that is a sensible part of the energy contained in the reactant, and this is the energy contained in the reactant because of its form, molecular structure. Okay, to form a compound from the element, you already spend some energy. So that energy is what is contained in the compound because of its molecular structure. You know, different molecular structure will have different energy required to form. So that energy is what is released during the combustion event. So the energy possessed by the reactants are of two forms. One is the enthalpy of formation based on its molecular structure, and second one is the energy associated with reactant due to temperature. Okay, that is called sensible energy. And this too will reflect in the form of delta U, which is change in internal energy, okay, of the reactants to product. That is what is Q R to P, and this is called heat of reaction. Q R to P is heat of reaction that is absorbed in terms of change in internal energy. Negative of heat of reaction is what this Q with the subscript C, and this is heat of combustion. Negative of heat of reaction is what is heat of combustion, Q with the subscript C. That is equal to UR minus UP. Change in internal energy of reactants and product is what is written here as heat of combustion in the case of constant volume combustion system. Now, if you look at constant pressure combustion.
So just 1 minute, sir. I'm sorry to interrupt. Sir,
Yeah.
you have told that heat of reaction is basically the summation of enthalpy of formation and plus energy released during the combustion, right, sir?
Yeah.
In a simple word.
Yes.
I want to write.
I will give more information about this in the next discussion, the next topic.
Okay, sir.
How you can arrive at U and enthalpy, I will give more detail. Here, just take note that heat of combustion is equal to difference in the internal energy in the case of constant volume combustion.
Right. Okay.
Okay. The case of constant pressure combustion, how you can visualize is you can visualize fuel and air flowing into the combustion system and products are leaving from the combustion system. So here you have this reactants entering into combustion system, products leaving the combustion system. So there is a flow happening here in a constant pressure system. Fuel and air goes into the system and products are leaving the system. So pressure is constant during this event, but volume is not constant during this event. Now, when you apply first law of thermodynamics, okay, first law of thermodynamics, Q R to P minus W R to P is equal to delta U R to P. Here, W is not zero because volume is not constant. So you will have a PdV term. You will have W is equal to PdV. In this case, dV is varying, pressure is constant. So if you expand this equation, you can write it as WR to P is P into dV, change in volume, which is volume of product minus volume of reactants. Okay, QR to P minus P, which is constant. This is a constant pressure system, but there is a volume change, Vp minus VR. That is equal to UP minus UR. And this can be written as QR to P is equal to UP plus PVP minus UR plus PVR. Why I have written this equation in this form, U plus PV form?
Enthalpy is equal to U plus PV, right? So
Exactly. So H is equal to U plus PV. That's why I'm writing this equation in this form, U plus PV form. So QR to P is equal to UP plus PVP minus UR plus PVR. And this can be replaced as H with a subscript P, which is enthalpy of product, and this can be written as H with a subscript R, which is enthalpy of reactant. So QR to P is equal to HP minus HRR. Negative of QR to P is HR minus HP, and you know negative of QR to P is Q with a subscript C, which is heat of combustion. So heat of combustion for a constant pressure process can be written as HR minus HP. Heat of combustion for a constant volume combustion process can be written as UR minus UP. The next topic I will discuss about how you can get this U and H, but this equation will give you an estimate of heating value under these two conditions: constant volume combustion condition, constant pressure combustion condition for any fuel. Okay, this is how you will get an estimate of heat of combustion of a fuel by applying first law of thermodynamics. Now, when you talk about heating value, there are two heating values that comes into picture. One is called higher heating value, and the second one is called lower heating value. This higher or lower value is based on the phase of H2O in the product, combustion product. Phase of H2O, here by phase I mean whether it is a liquid phase or it is a vapor phase. Liquid or vapor phase. So when a fuel combusts with the air, what will be the phase of H2O? Will it be liquid phase or vapor phase in the product?
Vapor phase, sir.
It will be in vapor phase. As a resultant of combustion, H2O will appear in the vapor phase in the product. Okay, as such, it remains in the vapor phase. Suppose, as per the conditions we impose, if you are cooling the combustion product to the initial temperature, what will happen to that vapor?
It will become a liquid.
It will become a liquid. Now, when a vapor becomes a liquid, how this process is happening? Conversion of vapor.
Condensation.
Condensation. So it liberates some thermal energy, right, during this process.
Yes, sir.
What is the thermal energy that is liberated?
Latent heat, sir.
Latent heat of vaporization.
Vaporization, yes, sir.
Liquid to vapor conversion, there is a latent heat of vaporization. From vapor to liquid conversion, there is a liberation of latent heat. For liquid to vapor phase conversion, there is an absorption of latent heat. The reverse thing will happen when a vapor is condensed to liquid. This is what will happen, and when you condense this H2O, when you condense this vapor phase H2O to liquid phase, latent heat will be liberated. If that heat is also added to the combustion product, then you call that as a higher heating value. So in higher heating value, H2O exists in the liquid phase in the product, meaning you are actually condensing H2O in the product to liquid, and during this process it liberates latent heat, and that latent heat is also added to the heating value. That is the case of higher heating value. So its value numerically is always higher. The other case is lower heating value, wherein H2O exists in the vapor phase. So you are not condensing it to liquid phase, meaning you are not recovering any latent heat when you talk about lower heating value. That's why its magnitude is less, and you refer it as a lower heating value. So you have these two terms, higher and lower heating value, and these two terms can be connected by using this equation, whatever I have written. Higher heating value is equal to lower heating value plus the heat that you recover by condensing vapor to liquid, which is what is written here in the second term. What is this number of moles of H2O into molar mass of H2O? What is this first term?
Capital N.
Mass of H2O.
Mass of H2O. And what is the second term? HFG, latent heat of vaporization of H2O. So basically you are multiplying mass of H2O with latent heat of vaporization of H2O. Okay, the denominator you have something NF and multiplied by M, capital MF. What is this denominator term?
Mass of fuel.
Yeah, mass of fuel. So why I am dividing this with mass of fuel? Because that is how you define heating value. Heating value is defined as kilojoule per kilogram of fuel, meaning thermal energy released by burning a given kg of fuel. That is equal to lower heating value. Again, it is kilojoule per kg of fuel that is burned. Thermal energy released by burning unit mass of fuel. And since you have added this latent heat with LHB, you have to add it in a consistent unit. That's what I have done here. M into H will give you thermal energy released by condensing vapor to liquid. This is divided by kg of fuel. That is what you have in the denominator. So you are adding kilojoule per kg of fuel in terms of latent heat to the LHV value to get the HHP, which is higher heating value. So by adding latent heat to the lower heating value, basically you are getting higher heating value. Okay, now you need to know what is the significance of this. Why I have to consider this? The H2O that is present in the combustion product in IC engine combustion system, okay, it always remain in the vapor phase. It is not going to be in a liquid phase. In IC engine combustion system, when you combust fuel and air, H2O is going to leave only in the vapor phase, meaning you should always consider lower heating value, not higher heating value, because you are not condensing H2O to liquid phase. But when you do the measurement with the bomb calorimeter, as I said, this is a measurable property. When you measure it, you are measuring it, what you are measuring is only higher heating value, not lower heating value. Because as I said, once you take fuel and air in a bomb and allow it to combust, the thermal energy released by combusting fuel and air in the bomb is absorbed by water. So basically you are cooling the product, combustion product, to the initial temperature when you do the measurement. Because of that, H2O present in the product will get condensed to liquid phase, and that heat is also added when you talk about the thermal energy release. So along with the actual thermal energy release, you are adding the heat due to condensation of H2O to liquid phase. So what you measure in the equipment is higher heating value always. But what is relevant for IC engine system is lower heating value. That is why you need to know how to convert this into higher heating value that you measure into lower heating value. What you need is this formula. What you need is the number of moles of H2O, which you can get from the molecular formula of the fuel. Okay. So why this is important is based on this heating value, we are defining the first law efficiency of IC engine or thermal efficiency of IC engine. Thermal efficiency of internal combustion engines are defined by this equation. As you know, thermal energy is equal to work that is extracted by burning unit mass of fuel with respect to thermal energy that is released by burning unit mass of fuel. Thermal energy released by burning unit mass of fuel is nothing but heating value. Right? So in an energy conversion device, which is IC engine, you are converting that thermal energy into work. Basically, in the first law equation, efficiency equation, you are relating output by input. What is the output? Work that you extract. What is the input to get that work? Thermal energy from the fuel. So you relate this to get the first law efficiency of IC engine, which is what I have written here. This is also called thermal efficiency equation that you use, which is one of the important parameter when you analyze IC engine. This is one of the important engine performance indicator, thermal efficiency. This work is not measured in an engine. What is measurable from an engine is power, right? So you can express this equation in terms of power. Efficiency is equal to power. How did I get this power? Power is obtained by multiplying mass flow rate with W, numerator term. Denominator is also multiplied with mass flow rate. That is what you are seeing. The second form of efficiency equation, which we frequently use when you calculate thermal efficiency. This power can be indicated power or brake power, as you know. It is based on what context you analyze engine performance. It can be brake power based or indicated power based. So this power is measurable. Brake power, you use a dynamometer to measure the brake power. Okay, it's a measurable parameter. That's why, but work is not directly measurable. That's why you always use this equation to calculate thermal efficiency in terms of measurable parameter. How it originates? It originates from this parameter, heating value. So this is one of the important parameter which help us to find important performance metric, which is thermal efficiency. Okay, this is the significance of this parameter. So, and the other important point you have to note down is, when you talk about heating value here in IC engine context, you have to use a lower heating value, not higher heating value. But when you use a bomb calorimeter, you are actually measuring higher heating value. Okay, so you have to convert that into lower heating value when you do your thermal efficiency estimate. This is an important point to note down. So to convert higher heating value to lower heating value, you have to use this simple equation. What you need to know is only about the number of moles of H2O. Once you know the fuel molecular formula, you will be able to get the number of moles of H2O. The rest of the parameters are known to you. Okay. So from this, you will have an estimate of lower heating value from the measured higher heating value, and that will help you to find the thermal efficiency more precisely.
So one question, sir, W upon QC, you written like P divided by MF into QC, right, sir?
Yes.
So W is equal to P into T, power into time, right, sir?
W is specific work.
Acha, like work per unit mass of the fuel, right, sir?
Always, because QC term is defined per unit mass, right?
Okay, that's why the MF has come.
You need to have consistent parameter when you divide one by other.
Got it, sir, got it. So that's the reason the MF has come in the denominator.
Yes, exactly.
Because
So to get power, you are actually multiplying by m dot. Okay.
Right, sir. Got it.
So numerator and denominator in the first equation are kilojoule per kg.
Right, sir.
The second equation, you are multiplying that by kg per second. So once you multiply kg per second, what you will get? Kilojoule per second. That is what is the power. Denominator kilojoule per kg. Kg per second is m dot f, and QC is again kilojoule per kg.
Perfect,
Okay.
sir. Thank you so much.
So I said we are going to get two parameters by applying first law. One is this heating value. Using the heating value, we have now discussed how we can get an estimate of first law efficiency, which is one of the important parameter when we do IC engine analysis to gauge its performance. So it is a performance metric, you say. It's an important performance metric, thermal efficiency, that we can obtain from heating value. And the important point for you from this analysis is you should use lower heating value when you do the thermal efficiency estimate. That will provide more accurate estimate, not higher heating value, which is what you are measuring. And you can also estimate heating value by using the first law equation, as I have just now shown. The next useful parameter that you can get from first law equation is adiabatic flame temperature, which is maximum temperature reached by the combustion product due to the combustion event. So we need to have an estimate of what will be the maximum temperature reached by the product. This is one of the important design parameter. So when you design an IC engine, you have to carefully design an engine in such a way that the engine is durable. So we know that IC engines are more durable. Typical lifetime is 10 plus years, right? It's durable. To make it more durable, you have to carefully choose the material. You have to carefully design the material. Design the engine, because it is subjected to high thermal stress due to the temperatures, high temperatures, and also temperature variation. Temperature variation poses thermal stresses, and the material and the design has to account for that. One of the useful or fundamental parameter that you need to fix the material or design an engine is how much is the maximum temperature reached by the products of combustion. This maximum temperature reached by the products of combustion is called adiabatic flame temperature. This you can get by applying first law. This is one of the useful parameter that you can get by applying first law of thermodynamics. Now we are going to see how we can get an estimate of this parameter, adiabatic flame temperature. As I said, this is a maximum temperature reached by the combustion products under adiabatic condition. The name itself implies that it's an adiabatic flame temperature. What is adiabatic condition?
Q supply is 0, sir.
So
Q supply is 0.
There is no heat interaction. There is no heat interaction between the system and the surrounding. That is what is adiabatic. So you can assume a situation where the engine body is thermally insulated. It's completely or perfectly insulated. So there is no heat interaction. This is an assumption. So why do we make such an assumption, and why do we get such an estimate? This is always, we always do design with the factor of safety, right? So we are talking about the maximum theoretical temperature, right? You need to have an estimate of theoretical maximum temperature. Actual value will be lower than this, but we need to have a estimate of theoretical maximum temperature so to design the engine, right? We always design it with the factor of safety. That's why we are discussing about a hypothetical or theoretical situation encountered by the engine where it is perfectly insulated. there is no heat interaction between the engine system and the surrounding. I mean, working fluid within the engine and the surrounding. That is what is the adiabatic condition. Now, under this adiabatic condition, if fuel and air, which is a chemically reacting system, if at all it undergoes combustion, how much will be the maximum temperature reached by the products of combustion? That temperature is what is this temperature. So when I talk about adiabatic flame temperature, there are several variables that influence its magnitude. Now, our focus is to get an estimate of this value, adiabatic flame temperature value, by applying first law of thermodynamics. So before I talk about the magnitude or value, temperature value, I need to know what are the variables that can influence this value. What are the variables that can influence this variable? So these are the variables. One is what kind of fuel that I use is going to affect the maximum value of temperature reached during combustion event. Can anyone tell me how the fuel type affect the maximum temperature value of the product?
If it is having less, what I mean to say is of energy density, value, and yes, sir. So like seconds per of.
So here you should note that octane or cetane is only to analyze the ignition. Okay, so here we are talking about the value, product temperature value. So,
Sir, it depends on energy density of the fuel. So
energy density of the fuel. Okay, calorific heating value just now we discussed. So it is going to be different based on fuel. Yeah, exactly. So you are talking about converting reactants to product, and you are talking about what is the maximum flame temperature reached by the product. This is what is adiabatic flame temperature. It's a strong function of fuel because the reactants, the product temperature or the thermal energy release is a strong function of what fuel you are combusting. Okay, different fuels will have different enthalpy of formation. So it basically depends on the compounds, multi-component mixture. We are talking here gasoline and diesel. Based on the composition of this multi-component mixture, the thermal energy released is going to be different. Accordingly, the adiabatic flame temperature reached is going to be different. So fuel is one of the important variable that affects the maximum temperature reached during the combustion event. Because the source itself is fuel. Based on the type of fuel you have, thermal energy release. What I mean here is gasoline will have different temperature, diesel will have different temperature. So suppose if you use an alternative fuel like methanol or ethanol, its combustion temperature, maximum temperature is going to be different. So this is one of the important variable that has a strong influence on the maximum temperature because the source itself is fuel, right? Energy source itself is fuel. So based on fuel type, you are going to have different flame temperature. Okay, so I will continue this. It's time up. I stop here. If you have any questions, you can. I can take your questions.
Sir, analysis of this heating value and this calorific value, and whenever we talk in terms of amount of energy released, we will be talking in terms of weight of the fluid, right, sir? Weight of the fuel, right, sir?
Weight rather than weight, you should say mass of the fuel.
Yeah, mass of the fuel. Am I right, sir? This?
Yes. Correct.
Okay. Thank you, sir. Thank you.
Yeah, correct. In fact, heating value is defined in terms of how much of thermal energy is released by burning unit mass or unit volume of fuel, unit mole of fuel.
Understood, sir.
Suppose if you have a gaseous fuel, the volume based will carry significant. Okay, liquid fuel generally we go with mass base.
Understood, sir.
Fine.
Thank you.
sir, one clarification required.
Yeah.
Sir, quiz 1 will be from the chapter 1, right?
Quiz 1, whatever contents we discuss until the quiz. Quiz 1 is on March 2nd, right? So whatever content we discuss until that Wednesday, the week.
Okay, sir. Okay, sir.
That will be considered as a syllabus. Basically, the purpose of conducting quiz is to get you familiarized with the contents that are discussed until the point of time.
Sure, sir. Okay, thank you, sir.
Yeah, thank you. So you know IITM has a continuous assessment, right? This is a general pattern that we follow. We have to continuously assess you to see your level of understanding, and the grading should be based on that. It should not be based
Got
on
it, sir.
one exam. Okay, that's why I go with 3 exam.
Got it, sir. Okay, sir. Okay.
Fine. That is a kind of fair evaluation of grading you.
Right, sir.
Understood, sir. Okay.
Right, sir.
Okay, fine. Because a lot of, I mean, some of you asked about 1 exam or 2 exam, right? So I'm saying
Yes.
you, what I am following is a standard pattern that is followed in IITM. So it is a continuous assessment. We need to check your level of understanding at each point of time when the semester moves on. That's why we generally have 2 exams, 2 quizzes, and 1 final exam.
Yes, sir. We understood, sir. Yes.
Okay, fine.
Thank you, sir.
So if there are no questions, I will stop here. I will see you tomorrow at 6 o'clock. Thank you.
Thank you, sir.
Thanks a lot, sir.
Thank you, sir.
Thank
Thank you, sir.
Thank you, sir.